Welcome, everybody. Welcome, Joop. Yeah, this is Joop Schaye from Leiden University, who is, well, trying to model the whole damn universe and give us an insight into why it is the way it is. Welcome, Joop.
Thank you. Yeah, it's a pleasure to talk to everyone, although I can't see you. But I'll tell you a little bit about the research we're doing here at my group, and that is rather ambitious, and that is to model the whole universe in a computer. And in the background, you can see already one of the results, but I'll come to that. All right, so let's see how I can go to the next one on this. There we go. Okay, so first a little sketch to see that we're all on the same page about what we mean by the evolution of the universe and what we think we understand roughly. So the model within which we are working, the standard model of cosmology, says that it all started with a Big Bang. What came before that, we don't really know. There was a really rapid expansion, very briefly. And then we don't really see that first very rapid expansion. And that is here, you can see it as the vertical extent, basically. So this is, we can't picture three-dimensional expansion. So this is just in 2 dimensions. So time goes from left to right, and expansion is the outline shown in the top. After a while, the expansion slowed down because of gravity. And then you can see towards the end, it says accelerated expansion. And why the expansion of the universe accelerated a few billion years ago, why it started accelerating, we don't really understand. I'll come back to that, but that is something we can observe. And what you see here schematically is the evolution of structure. So 300,000 years after the Big Bang is when we have the first picture of the universe, the baby universe. And what we can see there, and it's this color map on the left here, is blue and yellow and red map, is fluctuations in the temperature of the background radiation left over from the Big Bang. So that is nowadays very cold radiation. It's only about 2.7 Kelvin, 2.7 degrees above absolute zero. But it was much hotter in the beginning when the universe was compressed. We can see the temperature anisotropies with satellites, and those reflect the fluctuations in the distribution of matter very early on, when the universe was only a few 100,000 years old. And these small fluctuations, they grew through gravitational instability to the structure that we see today. And in the end, on the right, you can see galaxies, little pictures of galaxies. And in between, you see this web-like structure. And that is what we call the cosmic web. That's lots of little galaxies that are distributed in that manner. Right after this cosmic microwave background, you see it says dark ages. So this was before the first stars formed, but we don't have any information there because the cosmic microwave background tells us, that radiation tells us when the universe was 300,000 years old. When the first stars formed, we can see them, but in between we don't really see much. So that's why we call it the dark ages. All right, so this is the standard picture, and what we try to understand is how structure formed and how galaxies formed and why do they look the way they do. So here's the picture of the cosmic microwave background radiation. So what is shown here is an all-sky map in a projection that make it look elliptical, taken by the Planck satellite, and the color coding gives the temperature. So you can see that the temperature of the radiation field is not the same in every direction. There are small fluctuations, and they're actually really small, because I told you this temperature was about 3 Kelvin, and the color scale you see goes from plus 300 microkelvin to minus 300 microkelvin. So the standard deviation of these fluctuations is very small. It's only about 1 part in 100,000. And that is a lot smaller than the fluctuations that we see around us in the density field, because the density in our galaxy is much larger than the density in intergalactic space, for example. So what we think that happened is that these very small initial fluctuations, primordial fluctuations, grew through gravitational instability. If there's a little bit more matter in one location and there's more gravity there, then you get inflow of more matter, you get even more gravity. So it's a runaway process. And from this picture, we can measure then the distribution of the density fluctuations early on. And here's an example of this. Exactly what I plotted here, it doesn't matter too much if you don't understand this, but I'll say it briefly. So on the x-axis is basically the inverse of the angle between two directions between which you measure a temperature difference. If the number is 1, then that's the monopole. That's the same everywhere. If it's 2, then you divide the sky in 2 directions, so they're 180 degrees apart. If number is 100, the multipole number, then you divide the sky in 1,000. Oh no, sorry. If it's 100, you divide it by 100. So on the right are small scales, angles that are close together. On the left are large scales. And then the y-axis is the temperature difference between those directions on average. And you see this particular pattern here emerging, which why that looks like that I won't go into today. But what is interesting is that the line is a theoretical model, and the red points are the measurements from the Planck satellite. And you can see on the right, you don't see any error bars, and that is because the error bars are smaller than the size of the points. So this pattern is really well measured, and it's very well described by our cosmological model. And from the exact height of these different peaks, we can measure things like how much matter is there in the universe, how old is the universe. And what we learned from this is that the universe is a bit strange. So if we show here what dominates the energy density in the universe, and what you can see is that the ordinary matter, that's the protons and the neutrons and the stuff that you and I are made of, is only a few percent. That's this little red wedge. A much bigger fraction is what we call dark matter. We do not know what dark matter is. So it's hypothetically some particle that we still haven't discovered. But we see its effect through gravity, not just in this pattern of the cosmic microwave background radiation that we were just looking at, which probes the first few 100,000 years of the universe, but also in, for example, in how fast galaxies rotate. If there was no dark matter inside galaxies, then the stars would not stay in their orbit. They're rotating too fast to be kept in their orbit by the gravity of the stars that we see. So but we don't see this matter, that's why we call it dark matter. So it must be very weakly interacting with ordinary matter and not produce much light. Then the biggest bit of this wedge is what we call dark energy. And that is what's responsible for this accelerated expansion of the universe that we see at late times. And we have even less idea what that is. It's not a particle, it's some strange substance that has a negative equation of state. The pressure is a negative function of the energy density. We really have very little idea what that could be. So we are in a strange situation that we have a model that only has a few parameters and can reproduce a lot of observations, not just the one I just showed you, but many more, but we do not understand its constituents. Then if we look at the ordinary matter, the red wedge, and we ask, what is that? Only a small fraction of it is stars. That's the blue on the right part of the pie diagram. Most of the ordinary matter in the universe is not even in galaxies, it's in between the galaxies. The density there is very low, but the universe is so big that a lot of volume with very low density is still a lot of mass. Another way we can describe what this ordinary matter is, we can ask, what are the elements? What elements is it made of? And you can see about 3/4 is hydrogen, the lightest element, and about 1/4 is helium. And that helium was produced in the Big Bang, in the first 3 minutes after the Big Bang, when the universe was so dense and hot that it was one big nuclear reactor converting hydrogen into helium. But it didn't finish the job because the universe expanded too quickly. And the remainder, which on the average over the whole universe is much less than 1%, is the carbon, the nitrogen, the oxygen, all the heavier elements that on Earth we are very fond of and that we exist, except for hydrogen, we exist mostly of that stuff. All these other elements, they were made also in nuclear reactors, but not in the Big Bang, but in the insides of stars. So not our sun, because our sun is still converting hydrogen into helium. That's how it's powered. But more massive stars, they can produce also carbon from helium and nitrogen from carbon and all the way up to heavier elements. So before the solar system was formed, there were already other stars that formed these heavy elements. And at the end of the star's lifetime, probably multiple stars, those heavy elements were thrown back into the gas in our galaxy, and from these gas clouds, new stars, including our solar system, formed. All right, so what about the formation of galaxies then? How did that come about? Well, we think we started with these primordial fluctuations that we can see in the cosmic microwave background. And at that time, the dark matter and the gas, the ordinary matter, were pretty well mixed. Gravity then magnified the fluctuations in the density, and the expansion of space tries to go against that, right? Because what happens with the expansion of space, if it is very fast, it tries to stretch out the density fluctuations. Think of the Earth and a mountain on that. If you would blow up the Earth, then the mountain would seem to shrink, right? It would get stretched out. But gravity can win if the fluctuations are large enough. And then what you get in the end is you get quasi-spherical distributions of dark matter, where in the end, the collapse is stopped by the random velocities of the dark matter particles. You also get gas. It gets hot because it gets compressed by gravity. And it's still mixed relatively well with the dark matter on that scale. This is a scale that's still bigger than the galaxies that we see. What happens next is we again want gravity to compress the matter further. For the dark matter, that doesn't work so well because it cannot get rid of its random motions. For the ordinary matter, that does have a way to get rid of its energy, and it is by emitting radiation, because it does interact electromagnetically. And as it emits radiation, it loses energy and is able to get full collapse further under its own gravity. Before that, gas pressure was stopping the collapse of the ordinary matter. In the end, the collapse gets halted usually by the centrifugal force, which only works in one direction, the direction of the net angular momentum, and that's why galaxies are often disky. And then within this disk of gas, you get a similar process where solar systems form, stars form. And all of this together, this halo of dark matter and hot gas with inside it a disk or a distribution of stars and interstellar gas is what we call a galaxy. Okay, so that's a little bit of background. So what are the kind of questions we are investigating as a community? We would like to understand the statistical distribution of these primordial density fluctuations. Many of them we can only infer indirectly. We can see some of it in a microwave background at a particular time, but not on very, very small scales. Most of it we need to infer from looking closer to us, to the distribution of galaxies, and then working backwards with theory to see what the starting point was. We'd like to understand how this large-scale structure, this cosmic web along which galaxies are distributed, how did it emerge? And when did the galaxies form, and how? And why do we have galaxies that are disky? Some are more round, some are big, some are small. And how do these galaxies know how many stars to form? And how much of a black hole in the center they need to form? Because almost every galaxy has a massive black hole right in its center. And it seems that the existence of this black hole actually influences the growth of the galaxy. So how does that work? Well, we study, and others too, study a lot of these questions using simulations. Why do we use simulations? Well, there are several reasons. One is that it's hard to do laboratory physics in cosmology. You cannot form a galaxy in a lab. So there are numerical experiments, the simulations. The other problem we have with astronomy is that the timescales are astronomically long. So a galaxy doesn't change on the timescale of a human life. It takes hundreds of millions of years to change typically. So we can't just wait and see it evolve. So with the simulations, we can speed things up. So the simulations are used to test theoretical ideas. Right? We code up our ideas and see what comes out. If we have a good theory, quantitative theory, then that has some parameters. For example, the standard cosmological model, a parameter is how much dark matter is there in the universe, how much dark energy is there in the universe, how much ordinary matter is there in the universe. Then we can run simulations that vary these parameters, compare the predictions with the observations, and measure the values of the parameters of the model. Another important application is that when we observe the universe, it's hard to see what's going on often because we often see only the tip of the iceberg, the brightest bits. There's projection effects. We don't see it. We don't in 3D. We don't know the distances very well. And there's various other complications. So we can make a virtual universe from a simulation, and that can help us guide the interpretation of what we see in the real universe. So it's a back and forth between theory and observation that way. And when we develop techniques to analyze galaxies, for example, think of classification of galaxies using machine learning. We can train these things also on the simulations, provided they're realistic enough. We can test ideas for new observing strategies, for example, as well. And as we'll also see, they're very useful for visualizations, which gives us intuition, but it's also very good to use for teaching and public outreach. The simulations we do are cosmological simulations. What do we mean by that? So that just means that we simulate a part of the universe that is representative. So if we're interested in galaxies like the Milky Way, which is our galaxy, that we want to simulate a volume large enough that there's many such galaxies in that volume. So it just needs to be much larger than the objects of interest. And what are the ingredients? Well, we start with a cubic region of space, and we do that because then we can give it periodic boundary conditions. And that is important because if we do not do that, if we have a vacuum next to the piece of universe that we're simulating, then we get edge effects. Then the expansion of the universe is done basically via a coordinate transformation. Right? We can solve the coordinate transformation analytically using the equations describing, basically from general relativity, describing the expansion of the universe and implement it that way. Then we discretize the stuff in the universe using particles, where each particle represents a lot of matter, which can be dark matter. Then we have dark matter particles or ordinary matter. And how much matter there is in one particle depends on how big a volume we simulate and how big a computer we have to do the simulation. But a typical number you can keep in mind is like 1 million solar masses of matter in one resolution element. And a resolution element is then a particle. The initial conditions. So what is the starting point of the simulation? This cosmic microwave background radiation that I showed in the beginning is an important one, but there are other ones. But these are pretty good. They're pretty well constrained at these times. And then we just solve the equations of physics, which is gravity, hydrodynamics, so gas pressure is important. Also, the emission of radiation is important. And for that, we need to do some atomic physics and even some nuclear physics sometimes. But there's other things that we cannot resolve. We only have a finite number of resolution elements. If your resolution element is 1 million solar masses, then obviously you cannot directly simulate the evolution of an individual star. So we need to model things that happen below the resolution limit of the simulation. And we call these subgrid processes. And examples are stellar evolution and the birth of stars, and also the formation of black holes.
So here's a question about boundary conditions.
Yeah.
So we have some observations of the universe, and they appear to be annoyingly, I mean, they go far back, but they're not in the same place. So it seems like we have a picture of the old universe in some locations, a picture of younger universes in other locations. So to what extent does that mess up our ability to constrain the bounding box of the simulation?
Yeah, that's a good question. So we make an assumption. We always start in physics with the simplest assumption. So the first assumption people made is the universe is the same everywhere. And then it's very easy to solve. Well, that's clearly not the full answer, because otherwise we wouldn't exist. The next simplest assumption is to say it's statistically the same everywhere. So there are fluctuations, but they follow the same distribution, statistical distribution everywhere. And if you make that assumption, then it doesn't matter too much that you're looking in different locations when you're looking further or closer by, because you say statistically the region you're looking at is representative. Now that's an assumption that needs to be tested. That clearly does not work if you're interested in fluctuations on the scale similar to how far we can look, because then we only have one sample. But on the scales of galaxies, where galaxies form, those length scales, we have many different samples. We can chop up the whole sky in many regions that are big enough, and then we can average over them. But yeah, we cannot. So does that answer your question?
Yes, and because the assumptions are statistical, but it appears most of the large-scale simulations are very expensive, and therefore you have a few runs. How does that rationalize against, the assumptions are statistical, but the runs are, just a couple of samples?
Yeah, so that means that there's always a compromise. So if you want to study very large objects, which probe large length scales, then you need a volume that's still much larger than the object so that you have a statistically representative sample. But then with a finite amount of computing resources, that means you have to go for low resolution, so you can't see much detail. But we're not trying here, in this case, when I say we simulate the universe, we're not trying to simulate our exact realization of that statistical distribution. So we wouldn't get the Milky Way in the right location. We just get galaxies that are similar to the Milky Way with the right number and properties, but not individual objects in the exact location. Right, so the statistical distribution, we're trying to get the same, but not the realization of that statistics.
Okay, so I should be thinking statistics in space, not across many runs of possible realizations of the universe, but really different parts of the single run is the distribution we should be looking at. Yeah,
you can also do it the other way. You can do many different simulations that of the same statistical distribution that we sometimes also do.
Okay.
It depends a little bit on the application. Yeah.
Right. Okay, got it. Thank you.
Yeah. All right. So here's an example of one of these cubes. This is a somewhat older simulation. And this cube is the size here, you can see, is half a giga light year. So that's 500 million light years at the present time. But here I'm showing what it looked like when the universe was 7 times smaller than it was today. And now the color coding here is the density. So you can see kind of a cosmic web structure. If I now go fast forward to the present time, then you can see, and now the expansion of the universe was scaled out, right? So now it's 7 times bigger, really, this volume. But if I take that out and I go back and forth, you can see the same large-scale structures, but they are more prominent at later times because of this gravitational instability magnifying these density fluctuations. And here you can see clearly this cosmic web. Now, an individual galaxy here is smaller than 1 pixel, right? So we're looking at large scales. So this web would be the distribution of galaxies. So here's why we need these subgrid processes, because we need to, if we want to simulate the whole universe, we still have to worry about the small scales. So the size of the observable universe, which is how far light can travel since the Big Bang, is about 10 to the 28 centimeters. Very, very large. The largest objects that are collapsed objects are clusters of galaxies, right, that orbit each other. And those are about 10 to the 25 centimeters. Galaxies come in all kinds of sizes, but a typical number is about 10 to the 22 centimeters. But we also want to worry, we have to worry about the stars inside them, right? The stars, they form the elements. They also feed back energy when they go supernova, when they explode at the end of their lives. When massive stars explode, that dumps a lot of energy into the gas, and that's important, as we'll see. So then we have to worry about the sizes of stars, which are 10 to 11 centimeters. But when we want to see how much radiation is emitted by the gas in between the stars or in between the galaxies, then we have to do the atomic physics. We have to follow collisions between protons and electrons because that leads to the emission of radiation, and that's how the gas can cool and collapse. And then we're talking about centimeter scales or smaller. And when we want to do nuclear fusion inside stars, then we're talking about 8 orders of magnitude smaller scale still. So clearly this is too big a dynamic range, too big a range of length scales to directly simulate. So you always have to choose, what do you directly simulate and what do you model in a subgrid way? Okay, so an important concept is feedback in galaxy formation. And what we mean by that is that when stars form, they can prevent or stimulate further star formation. So we have a feedback loop. And what is shown here is the points here are observations of the number of galaxies as a function of the mass of galaxies, the number density of galaxies on the y-axis, and the mass of galaxies in units of solar mass on the x-axis. Our Milky Way, our own galaxy, has a mass of about 10 to the 10.7. So it's right about at the knee of this mass function where it starts to shoot down. And what is shown in the solid line is a simulation that we're doing now that can reproduce this quite well. So this is the stellar mass. But I've told you there's also dark matter in the universe. And these galaxies are hosted by quasi-spherical halos of dark matter. And they are more massive because the dark matter has more mass. What this dashed line shows is how many of dark matter halos there are as a function of their mass. And what you can see is that line is above, the dashed line is above the solid line. And since for each galaxy there is basically one dark matter halo, the horizontal shift between these two lines tells you about the mass difference. Now, in the whole universe, about 1/5 of the mass in dark matter, in matter, is ordinary matter. So I should say dark matter is about 5 times more abundant in terms of mass than ordinary matter. So this shift should really be a factor of 5 if the distribution, the ratio of ordinary matter to dark matter in galaxy halos were the same as that ratio is in the whole universe. But what you can see here is that it's a lot more, and particularly it's a lot more if you go to low mass objects. So those are the numerous ones on the top left, and also if you go to very massive galaxies, that's the bottom right. Whereas where the Milky Way lives, right about 10 to the 11 solar masses, the ratio is about a factor of 5. Maybe it's a bit smaller. So that tells us that galaxies that are much less massive than the Milky Way were very inefficient in forming stars. And the same is the case for galaxies that were much more massive than the Milky Way galaxy. And we think that is to do with feedback processes. When you have a very low mass galaxy and it forms stars, some of these stars go supernova, and that's gigantic explosions at the end of stars' lives, massive stars' lives, and that energy is then enough to eject a lot of the gas, which is the fuel for new star formation. And then star formation is inefficient. And in low mass galaxies, that works quite well, that feedback loop, because the potential wells are very small. There isn't that much gravity in a low mass galaxy, so it's quite easy to eject the gas. Then as you get more massive, that ejection gets more and more difficult until you get to a mass similar to the Milky Way. But then something else changes. And what we think there is that a different feedback loop takes over. And that has to do with the supermassive black holes that live at the centers of these galaxies. As gas spirals into these black holes, it gets really, really hot due to friction. And as it gets really, really hot, a lot of energy is emitted in the form of radiation. And there's also some magnetic effects. And these things can also blow out the gas out of the galaxy. And that works even more efficiently than the stellar feedback. So that basically shuts down the star formation. That's the hypothesis. And that's why then the number of density of galaxy plummets towards higher masses. Right? But this is the broad question. Yeah?
The first one made perfect sense. You have small clumps of matter. One nova blows out the whole area. You have density is too poor. Second one is a bit confusing. You have a supermassive black hole. It doesn't eat the galaxy. It seems like it just heats up enough gas and then blows it out again, starving it.
Yeah,
something like that.
It's indeed strange because the black hole is actually only a 0.1% of the mass of the galaxy, right, typically, of the stellar mass. But this process of as gas spirals into the galaxy, it loses about 10% of its rest mass energy that's emitted. So it's very efficient because the rest mass energy, that's the E is mc squared of Einstein, has a lot of energy per unit mass. So a little bit of mass feeding that to the black hole, that on its way into the black hole loses enough of that mass, is converted into energy, that it's actually a huge amount of energy, enough to blow out the gas in these massive galaxies. And in the question then is, why doesn't this happen in the lower mass galaxies, for example? And that is apparently the black holes do not grow as efficiently there. Why? We're not sure. Maybe because of the stellar feedback preventing gas going into the black hole, but there's other ideas. So there's a lot of these aspects of this picture we don't fully understand, and that's why we do this research. But this is the standard hypothesis. Yeah.
Okay, so if I were to summarize, then it's small galaxies. You have individual novas are small bombs that are very effective at killing the small galaxies. Very large galaxies, they grow extremely large bombs that are able to blow up such a large galaxy. And in the middle, none of these happens.
Yeah, in the middle, it's the most efficient forming stars because the supernovae are energetic enough to overcome the gravity. Then the black hole starts growing, and as that is massive enough, it gets these very dense gas streams around it, which emits lots of radiation that also eject a lot of gas.
Cool, thank you.
All right, so one of the I'm going to talk about two simulation projects, and one of them here is the FLAMINGO project. And this one is aimed at cosmology, which means the properties of the universe as a whole. So not so much the formation of individual galaxies, although that's simulated as well, but more the large-scale structure. And the basics of this, the details don't really matter, is that we do form the galaxies. We have some free parameters in this, particularly this efficiency of these feedback loops. And what we need to do then is we need to choose some observation to calibrate our free parameters on. And there's two observations we use for this. One is how many galaxies are there as a function of their mass, and that basically sets the efficiency of the supernova feedback. And the other one is how much gas is in clusters of galaxies as a function of their mass. So a cluster of galaxies that orbit each other around their own gravity. And that one is important because it depends mostly on the efficiency of this black hole feedback, because that is energetic enough to eject gas even out of clusters of galaxies. And it's also important because that is a bottleneck, that's a limiting factor when we try to measure the properties of the whole universe, and I'll come back to that. The size of these simulations volumes is large. It's a good fraction of our observable universe. It's a few billion light years on a site at a minimum. That means the resolution is fairly low. It's about 10 to the 8 solar mass or less per resolution element. Lots of particles, lots of resolution elements, about 300 billion. And we don't just do one simulation, we vary all kinds of things in it that we don't understand to see what the effect is. Here's a video. I think this one is going to play over the stream because not that much changes. So this is the whole volume of one of these simulations. We're starting when the universe was 16 times smaller than today. I haven't started it yet. So, and on the left, you see the whole volume. On the right, you will see a zoom in of the center. And what we're going to see in the color coding is how much matter there is per unit area. So in the beginning, it seems it's almost the same color. So I'll start it now. And that is because the fluctuations are still very small. Our time is going forward, and we see now that gravitational instability is magnifying these fluctuations. The expansion of the universe has been scaled up, right? So really the universe is getting bigger and bigger here. And if you look on the right in the zoom in, you might start seeing actually the stuff moving. For example, on the bottom, you can see it collapsing under its own gravity, right? And a galaxy is again much smaller than a pixel. And what you see here is this cosmic web. And at the nodes of this cosmic web where the filaments intersect, that's where we have big clusters of galaxies. On the right, you can see that there are structures as large as basically this inset. But on the left, you can see that this box is big enough that anywhere you put a square like that, you get roughly the same type of density fluctuations. So this is for studying the large-scale structure.
Then question from chat. So you have there's a lot of self-similarity going on in the universe, and you showed like a bunch of like large-scale, like different scale pictures that look kind of similar. And I'm also seeing same filaments like pattern both in a fine grain and a coarse grain view. So to what extent is that a pattern in the universe?
Yeah, it's there is some self-similarity indeed, particularly gravity. When you do only the dark matter, gravity is the only force. The initial conditions were close to scale-free, Gravity doesn't have a preferred scale, so it still stays close to scale free. When you put an ordinary matter in a picture, then on smaller scales, where the ordinary matter differs from the dark matter, I'll show that, is not scale free. And that is because ordinary matter knows about, for example, the age of the universe, because it matters whether the gas radiates fast enough to lose its energy within the age of the universe or not. So then it gets more complicated, and the scale-free aspect is broken. I'm going
So to what extent is that true for the cosmic web? What is that more of a what's called electromagnetic process or gravitational or both?
That's more of a gravitational process. Okay. Yeah, and I'll show this right here where you start seeing the differences. So on the left is the dark matter, and this is a much smaller region. So this region is about 300 million light years on the side. So it's a small part of the previous simulation. On the right is the ordinary matter, and it's the same bit of universe. And what you can see now is that you do see differences. They follow the same kind of cosmic web, but it's a lot more vague on the right side, as if you're wearing the wrong glasses. And that is because the gas feels pressure, whereas the dark matter does not. So it's smoothed out. It's a smoothed out distribution. Plus, these feedback processes, particularly the black hole feedback, can eject gas out of the centers. And this difference between these two pictures is something that we can actually measure with observations now. So our observations are getting good enough, for example, through gravitational lensing, to measure these differences, which also means that we're sensitive to these feedback processes. And it turns out if we do not understand these feedback processes better than we do today, then we can't really make much progress also with measuring how much dark matter there is in the universe and things like that, because we need to go to the smaller scales. That's what the new satellites, like the Euclid satellite of the European Space Agency, are going to measure the distribution of matter on smaller scales. But on these smaller scales, it matters whether you're looking at dark matter or gas, and we're sensitive to both. So we need to understand that better.
Got it.
I'm going to skip this and go to the next simulation project, which is more, this is called COLIBRE. This is very recently completed. And this is now studying smaller volumes at higher resolution. So the lowest resolution is the biggest box here on the right. And that's a factor 10 to 100 higher than the previous simulation, higher resolution, meaning factor 10 to 100 lower mass per resolution element. But the volume is also smaller. And if we then go to the smaller and smaller boxes, we get higher and higher resolution. And in these kind of simulations, you form quite realistic galaxies. And I'll show some, I already showed some example. I'm going to skip this too, and this one, and go straight to this picture. So here's another piece of cosmic web on the left. Now the color coding shows again the surface density, but a different color scheme. And you can see this a lot smaller. The bar there on the top left shows you 20 million light years. Before we were looking at billions of light years. And you see a piece of cosmic web, and now this web is, the structures are as big as the box. So that's the disadvantage when you go to a smaller volume. What is shown on the right is two insets zooming into two galaxies. So this is two individual galaxies, where on the right we show the stellar light, including attenuation, absorption by dust in the galaxy. And that's these dark bands. You can see it particularly on the bottom right, which is a galaxy that's shown edge on. So this is a flat galaxy, not too dissimilar from our Milky Way, also similar mass. And on the top, there's a galaxy that we see face on. On the bottom, we see edge on. And edge on, you see this dark band through it, and that's dust absorption, dust between us and those stars. So it's like you see the stars in silhouette. So you can see in these kind of models, we can study the properties of the galaxies. And we form all kinds of galaxies. If there's any one of you who've read some maybe popular astronomy books, you may have learned about or read about Hubble's tuning fork. Hubble, a century ago, classified galaxies, and he had this tuning fork to help the classification, where elliptical galaxies were on the left and this galaxy is on the right. And you can see we form all these kinds of different galaxies. Here, every galaxy is shown twice, once face on and once edge on. I'm going to skip this one too, because I'm going to show a video now. Now, I think what I should do, because I tested this, is go out of the PowerPoint and share instead another window, because in PowerPoint this video doesn't play so well. So I'm going to stop the sharing and share another window.
Excellent.
Okay. All right, can you see this one? Yeah.
Yes.
Okay. So this is a website that has all kinds of nice interactive visualizations, including also some videos. Now, what I'm going to show now is a video with sound. So this is going to be the evolution of one galaxy. We form thousands of galaxies, but this is just one that has a mass similar to our Milky Way at the present time. We're going to start much earlier, when the universe was much smaller. And we're going to see the stellar light with also the dust attenuation.
And question, what's the size of a particle here?
The particle is about 10 to the 5 solar masses here.
Okay.
And so in the inset, you see a larger scale view. That bar is about 300,000 light years. And then the bar on the big view is only about 30,000 light years. We're starting when the universe was only 1 billion years old. Now there's going to be sound. One sound is a ticking sound, which is visualized on the top right, and that is how fast the black hole, how much the black hole is eating. The middle panel is a melodic sound. The middle on the right visualizes that melodic sound. That is how many stars are formed per unit time. And the bottom right, that shows how much energy is injected and blowing out of the galaxy center from supernovae and black hole feedback. That is a wind sound, a whoosh. Okay, let's start it. So in the beginning, not that much happening. We see little galaxies falling into each other. What we're seeing is stellar light. It's very blue, stars. What you hear mostly the star formation rate as the melodic sound. When two galaxies merge and they fall to each other, there's a fuel, and you get a little bit of a pickup of the star formation. You heard the starburst, and you heard the wind whoosh. You hear the wind. Star formation means blowing out these galactic winds into space. The black hole is starting to do something as well as a big tick. The universe now is about 5 billion years old. If you look at the inside, show the larger scale, these big tidal arms. These are galaxies that are pulled apart by the tidal force, the gravity of the central galaxy. Black hole is now getting very active. Here, a very big storm. A few big bursts of energy injected by the black hole that blows so much material out of the galaxy that now is going to go into quiescent phase and form stars at a quite steady rate. So early on, there were a lot of mergers between galaxies that created a lot of star formation and black hole growth. Now it's more self-regulated through these feedback loops. Now the universe is about 8.5 billion years old. Dark you see is dust attenuation of the stellar light behind. Blue and the white is the stellar light. Nothing much happens now until there's some more galaxies falling in. And it's actually not too dissimilar from our Milky Way. That's also the last billions of years have been forming stars at a very steady rate.
And this would be from the rest of the cosmic filament, new galaxies show up as the thing contracts.
That's right, yeah. So if you would zoom out and show not the stars, but the gas, you'd see the filaments. Now it looks not too dissimilar from our Milky Way. Our Milky Way is actually falling into another galaxy that is slightly bigger, called the Andromeda galaxy. It's is going to merge with us probably in the future, in a few billion years. Something similar is going to happen to this galaxy, coincidentally, because we didn't try to simulate the Milky Way. Oh, there it comes. Fortunately, we reached the present day before it has time to come back in March.
Wow. So we did not, unfortunately, hear the sound, but it was beautiful. I mean, it was like poetry in motion.
Ah, okay.
And we'll have in my notes, I'll include the link to the site, because I'm glad you actually have it that posted so easily, because I think everybody should watch this.
Okay, the sound is a shame. I should, if I'd known, I think I probably forgot to click the share sound. I'm not so used to this interface.
But, yeah, but that's fine. No, this was beautiful. Like just visually, like the drama.
The sound is actually quite nice, I have to say. So, and I would listen to it with the headphones if you can.
Yeah.
Now, so I could stop. I think I should stop here. There's more videos here. There's a cluster of galaxies forming, for example. So you can look at our website. We'll post a link then underneath the thing. And I'll show just one more slide with my conclusions, but then I'll have to stop sharing. Where is my window? Stop sharing. Okay. The other videos are shorter, if you were wondering, but let me go back to this one and then go to my conclusions. No, that didn't work. Yeah, here we go. Okay, so these kind of simulations, cosmological simulations, they do a decent job at broadly agreeing with the observations. But there's a lot of things we don't understand. First of all, we do not understand what the dark matter is and the dark energy, the main components. But also, in terms of the galaxy formation physics, we don't really understand these feedback loops, both from the supernovae and from the black holes. When we compare the data, there's also discrepancies that I didn't have time to go into, but we clearly see the limitations of our models. So what do we need to do to go forward? Well, we're always trying to do things with better codes and bigger computers, so that allows us to either increase the volume or increase the resolution. We have to do much more work in really creating virtual observations and mimicking all the observational facts so that we can do apples to apples comparisons. The simulations I showed you did a very simple approximation of how radiation is transported through ordinary matter. That needs to be done more accurately. We ignored the existence of magnetic fields. We need to vary the assumptions on dark matter and dark energy, so we can see if we can observationally distinguish them. And of course, always, as we go to higher resolution simulations, then some of the things we do now in a subgrid sense, we can then actually do directly. So that's also the goal. And I'll stop there. Thank you.
Excellent. Thank you very much. So one I guess challenge these days is the different estimates of cosmic age and the cosmic distance ladder. To what extent can simulations clarify kind of the measurement anomalies we're seeing? The measurement of anomalies? Yeah, so you have different ways of measuring the distances to various stars in the age of the universe.
Okay.
And to what extent, that pollutes the boundary conditions you're seeing, and that you can, highlight which might be right or wrong.
Yeah, no, indeed, there are controversies at the moment to do with the distance ladder that, for example, feed into the value of the Hubble constant, which tells us how fast the universe is expanding. Some of that particular discrepancy we do not have too much to say about, and the uncertainties associated with that are important for this large-scale distribution. So these first simulations I showed, but they're not so important for the galaxy scale simulations. But there are other discrepancies between different observations where we directly play a big role with the simulations. For example, how much gas there is in these clusters, how much is ejected by feedback processes. If we look with different types of observations, then we get different answers, and we don't really understand why at the moment. But the simulations can help understand that, but then we have to do this virtual observations and to see what are the systematic errors that each type of observation is making.
Okay, and so to what extent are ultimately the assumption that goes into observations are modelable, and they go to some model. Should I be thinking of more of a statistical model of observation error, or more, dynamic models that you're working on?
Both are important. So we need to vary the assumptions as well. If some measurement of our boundary conditions, you said our initial conditions, is uncertain, then we vary it a little bit within the uncertainty and see if then we can predict differences that are measurable using some other kind of observation. And that way we can help see what the right answer is. But vice versa, the observations often have limitations that we're not quite aware of until we start modeling them in detail. So mimicking the observations using virtual data. And there we can give insight into systematic errors that may have been overlooked.
Right. And I'm noticing that the finer resolution models, so 10 to the 5 solar masses, they're still quite large. Is that fine enough to capture things like, supernovas that usually have some stellar wind pushing things out, or is that's still a subgrid process?
That's a subgrid process for these simulations. So when supernovae go off in these simulations, it's not one, but it's many at the same time.
Mm-hmm.
And that can be important. So what we do is we vary the resolution, and we see, do things change if we increase the resolution? But we can't do this we can only do this up to a point. Other groups, and some of that we do ourselves, are zooming into individual galaxies. Then you can use much higher resolutions. Then you can look more at what actually happens when supernovae go off. And that knowledge that we gain from these very high resolution simulations of sometimes even a small piece of a galaxy, we can use to design subgrid models for the lower resolution simulations.
So then what are the techniques to do that coupling? Because what you'll ultimately have is multi-scale physics down to quantum, if you do the latter far enough. But should I be thinking of you design an approximation based on a training data set of fine-grained simulations, or call the fine-grained simulations, or some hybrid of the two?
Both of those approaches are taken. Also, observations sometimes feed in directly, because we can also observe in detail small scales, or just theoretical ideas that we can just put in equations. But this is the point you raise is exactly where all the discussion and debate is, and the state of the art. How do you couple these scales, and what do you do about the things you cannot resolve? And that is not always clear what the right answer is. So different people take different approaches.
Okay, so working up the methodologically, like what the trade-offs are. There's the more machine learning-y things where if you have a big enough data set of subscale observations, you can train a blind model because you have enough data. Or more like differential equation, where you have, if your data poor, you have to put a bunch of assumptions about the possible dynamics and really just vary the structural forms. Which mode are we in a lot of these problems?
Well, for example, for these large-scale simulations that I showed at the beginning, we actually used machine learning to do the calibration of the subgrid model. Okay. So we did a bunch of somewhat smaller simulations, made an emulator based on those, and fit those to the result with that of those emulators to observations. So that's one approach that we've taken. But that doesn't always work. If your model is crap to begin with, then using machine learning on it is not going to help. So it's a back and forth with different approaches. In the end, what ideally we'd want to do is to do simulations on all kinds of scales and have the highest resolution simulations feed into the next level and inform us. But that also doesn't work very well. It all works to some extent, but it's also not the perfect solution. Because when you have these winds coming out of galaxies, the way they interact with the medium around the galaxies is itself not well resolved. So it's not like it's only the highest density regions that are unresolved. There's also the hydrodynamic instabilities, for example, between these outflows that can be important. So there you might also need some subgrid models, but that's everywhere in your volume. So you have to be clever about it in the end and try to really figure out what are, for the particular question that I'm interested in now, for this problem, what are the most uncertain ingredients? And then you say, how can I constrain those the best and vary what I still don't understand? But the design of these numerical experiments, therefore, is tricky.
Okay, so then maybe the last question is about much of machine learning is, you have a structure or a statistical, structure of a process, and you tune its free parameters, and whether it's called neural net, little structure, a lot of parameters, or something else, which is a lot of structure, few parameters. But now, as we have more generative, coding, then you can actually write brand new equational forms and just say, try this, and just the code will come out. To what extent is that functional, and to what extent can you evolve your theories in code and explore that space with this style of ML?
Well, there's different approaches taken. So what is most common in this field is to build emulators, either using neural nets or Gaussian emulator, process emulator, or something else. There's other things that are being done to, for example, on the simulation output, you can also train machine learning algorithms to produce something else. Or, for example, to speed up the simulations, to simulate the outcome of things that are too expensive, instead of simulating directly to immediately jump to an answer. The question is quite general, so I'm not quite sure how to...
What I have in mind particular is like Google has anti-gravity, there's Cloud Code, there's all these things that just like, I describe equations and just give me code. Make five new flamingos based on the latest theories or guesses, right? It's not a normal kind of ML. You just have a new structural form that you're exploring.
Yeah, what is
functional? What changes?
Yes, what we do is, for example, teach the machine how to go from the initial conditions to the answer without doing the whole simulation. And that can work in some context. So it depends on how much precision you need and how much detail you need. But this is just at the beginning. So people are starting to experiment with these techniques. A lot more is possible. And in terms of changing the equations, the fundamental things, not as much has been done. More about the ingredients and varying the amounts of the different matter, for example. The equations themselves haven't, because it's mostly because the equations of general relativity are quite well established, and there is this very simple physics, hydrodynamics. But the equations of these subgrid models, for example, are good candidates to do some more aggressive variations, because they're not as well physically grounded. They're all approximations anyway.
Right, got it. When you're simulating things directly, that's established physics. When you're doing it like subgrid indirectly, that's when it's the choice of the approximate equations that's, well, widely variable.
Yeah.
Got it. Cool. Well, thank you very much. It was fascinating and dramatic, actually.
Yeah. Okay. Well, I'm very happy to do this. I'm sorry that I messed up the sound, because I knew I had to be on, but it was. I
actually appreciate that you have them. Like, that's highly unusual and like very, very interesting that you actually incorporated sound into these simulations.
Yeah,
I've never. This idea.
It's something new that I should say is done by. It was created by James Trayford, who was a postdoc in my group, and he's doing this both for inclusiveness, for allowing people who are visually impaired to do things, but in this case, it's just as an extra dimension for your senses.
Yeah, absolutely. It's like a planetarium, because these things are gorgeous. All right, cool. Well, then thank you. Have a great rest of your day. Thank you for joining us.
You too. Thank you. Bye-bye.